Okay, in this video I'm going to go over how to predict redox reactions giving a number of species here. So we're going to assume we have a tin bromide solution. It's being poured into an acidified solution of sodium dichromate. So what we need to do first of all is write out all of our things that are available, or all of the ions that are available in this chemical soup, and determine if any of those will undergo a reaction. So tin 2, so tin 2 there. Bromine, it says it's acidified, which means we have H+. Sodium dichromate, Cr2O7, 2-. If you don't know dichromate, you can look that one up, but I just happen to know it because because I was preparing for this. So that's all the things that we have to work with. Let's see if any of these things can act as oxidizing agents or reducing agents. Over here, I have tucked away my standard redox table so that I can look for things. So I'm going to start with tin. And remember that if he's on the left-hand side of this, that means that he is undergoing a reduction. And so what he would do to his partner atom is an oxidation. On the other hand, if he's on the right-hand side, that means that he's undergoing an oxidation if the reaction went backwards. And if he gets oxidized, that means he's acting as a reducing agent to his partner. Here I can see on my table tin 2 right there. So that guy can act as a reducing agent since he's on the right. I guess an easy way to remember that is there's an R for right and an R for reducing agent. Just taking a quick swing through this, make sure I'm not missing any more tin 2s. And I don't see any. Okay, bromine minus. He is on the right as well. So he is also a reducing agent. But I'm just going to make a little note here. So far this is the lower of the two. H plus sits only right here in the middle as an oxidizing agent, and if we look all the way up here we can see he acts with chromate as an oxidizing agent, and that's the two places that he appears. So he can work with him as an oxidizing agent, or he can be an oxidizing agent on his own. So that's where he appears in the chart. And just for what it's worth, we've noted that this one is the highest so far. Now sodium, all the way at the bottom, is an oxidizing agent. And I think that's going to be the only location of chromate here, but I'm just going to take another quick look. Nope, that's it. So those are my things. Bromine could act as a reducing agent. Tin could act as a reducing agent. Hydrogen could act as an oxidizing agent on its own or with chromate, and sodium can act as an oxidizing agent on its own. Now if I look at this carefully, I can see that remember that our strongest oxidizing agent is on the top left hand side, and our strongest reducing agent is in our bottom right hand side. So what that means then is that these guys want to get reduced the most, or they want to oxidize the other guy the most. Alternatively, these guys want to get oxidized the most, or they want to undergo the backwards reaction the most. So for the reducing agent, I'm looking for the lowest, and for the oxidizing agent, I'm looking for the highest. So with that in mind, I did label these as I went through. This one was the highest and this one was the lowest. I know that tin 2 plus is going to be my reducing agent, and chromate and hydrogen will work together as part of the oxidation. So what that means then is that this reaction will happen in its normal order as it's acting as the oxidizing agent, and this one getting oxidized or reducing the other one as the reducing agent will happen in the reverse. See, these are all naturally drawn as reductions, so the oxidizing agent naturally gets reduced. Cr2O7, 2 minus, I'm basically writing out this line right here, plus 14 hydrogen ions, plus, how many electrons? It's got to be a whack them. 6 electrons are going to become 2 chromium ions and 7 waters. And that is happening in that order. See, that's a reduction, or it's acting as an oxidizing agent. And in the reverse order that it appears, I'm now writing out this line. Tin 2 plus becomes tin 4 plus by emitting 2 electrons. Looking at these two reactions together, I can see that this reaction requires 6 electrons and this one is only producing 2. So that means I'm going to have to multiply this reaction by 3 to make sure that I produce the 6 electrons that I require. And then to write the overall reaction, I can cancel those two and I get chromium, or dichromate, plus a whole bunch of hydrogen ions, plus 3 tin atoms, turning into 2 chromates, 7 waters, and 3 tin 4s. Now a nice check for this is to make sure that the charge is conserved on either side of the equation. So I have a plus 6 here, a plus 14 here, and a minus 2. That'll get me a total of plus 20, plus 18 on this side, plus 6, and plus 12, totals to 18 on this side. And if my charges agree, chances are I have balanced my equation correctly and I'm done. So that is the resulting reduction-oxidation reaction that would occur if we mixed all of this stuff.